Factors we're going to be talking about is chemical factors. These are factors that we really need equipment or some sort of testing mechanism to figure out. It's not something we can just look at and see. And one of the most important ones is dissolved oxygen, or called DO, not DO, but it's called DO. And dissolved oxygen is literally the amount of oxygen that's dissolved in the water. This is really important to living things in the water. And it's also important for chemical reactions in the water. You need that oxygen to facilitate some of the chemical reactions that are important to living things. So if you think about aquatic organisms, and aquatic organisms mean organisms that live solely in the water. And if you live solely in the water, you do not have lungs. You need to make sure that you have oxygen in the water in order to survive. Zooplankton is basically teeny tiny water animals that you usually need a microscope to see. Fish need oxygen.
How do fish breathe through their gills instead of their mouth?
So whenever they swim, water flows over their gills, and when it flows over their gills, the gills filter out the oxygen and send it into their bloodstream. So it's kind of like what lungs do, except they don't breathe it in, it just rushes over the tissue. There's a couple ways in which oxygen can get in the water. One way is through diffusion. And diffusion is the natural movement of oxygen from the air to the surface of the water. So if you have nothing on top of the water blocking it, then the oxygen is able to be dissolved into the surface water, and then the movement of the water moves that oxygen into lower regions. In fish tanks, a lot of times, you'll see that they have these, what they call aeration stones, that are hooked to like a tube, and it pumps air through this stone and releases bubbles. And if you've seen Finding Nemo, then in the tank they had like the treasure chest that would pop open and release bubbles, and that fish go bubble, 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 bubble. That is putting gas into the water. It occurs naturally in streams, ponds, lakes. But in fish tanks, that's not a natural place. We need to help them get the oxygen into the water. Yeah. How you tripping you that? Also, if you remember photosynthesis, when plants undergo photosynthesis, the byproduct of changing that carbon dioxide into glucose and oxygen, byproduct is oxygen. This goes for plants that are living in water as well. So kelp, seaweed, seagrass, algae, any plants that grow in the water, they use photosynthesis too. And when they do, they release oxygen bubbles into the water. So you can get an aquatic plant from like the pet store, put it in a bottle and put the bottle next to the window, and you'll be able to see bubbles coming up from the plant, and that's the oxygen it's releasing. Woo! I'll drop that for real. The higher the dissolved oxygen in the water, the better it tastes to us. So that's like the difference between going to, I don't say soda fountain, but it is a soda fountain. Going to a soda fountain and getting fresh ice water versus having a cup left out for a few days, and then y'all take a sip and you're like, ooh, it's kind of stale. It's like water doesn't go bad. It doesn't expire, despite what bottling companies try to tell you. But once there's not a lot of oxygen left in the water, once it's been sitting out, it's not freshly poured, This starts to taste kind of stale, and that's because the dissolved oxygen levels are lower. The dissolved oxygen meter, if y'all remember me showing you the probeware back from the chemistry unit when we studied pH. The dissolved oxygen meter looks like this. It plugs into a computer, and all you gotta do is dip it in the water sample, swirl it around a little bit, and it's gonna tell you how much dissolved oxygen is in your water sample. Turbidity we can also use. We have a turbidity sensor, and it works a little differently than the other sensors. With the turbidity sensor, you have to follow directions carefully because it's a unit that you take the glass vial out of, and you put your test water in the glass vial and then close it up, and it reads the turbidity that way. You don't stick anything in the water. You put the water inside of the sensor. You good? All right, pH. This should not be new stuff that we're putting in your notebook right this second. This should be review. We've already talked about pH. pH is how acidic or basic a substance is. And just a reminder, if you take a pH reading and it comes up 0 to 6, that means it's an acid. If it comes up 8 to 14, it's a base. And if it's 7, it's neutral. If we have a sample of pure water, nothing added into it, no minerals or anything, then our pH should be 7. Most of our water does not come out as 7 because we have minerals or additives, especially in our tap water, that alter the pH a little bit. But ideally, drinking water needs to be between like 6.5 and 8.3. It doesn't need to be beyond any of those measurements, otherwise it's not really safe to drink. So if you go out in the field, you go to a pond, and you stick your pH sensor in the water, and it comes up saying a pH of 3, I wouldn't drink it. You might as well be drinking battery acid. That's very acidic water, and there's not going to be a whole lot that's alive in that water. The pH level also determines the presence of other materials. So, depending on the pH, depends on how much iron you read, or how much mercury you read. So that controls how much of those substances are showing up in the water. We will be using a pH sensor to test the pH of the water samples. It's really easy to use. But for the next two things, you're not going to be using a computer for. You're going to be doing chemical analysis. One is for nitrates, which has to do with nitrogen. And the way we test for nitrates, the way we're going to test, is instead of using sensors, easiest way is to use this aquarium test kit. So you gotta test the nitrates in your aquarium to make sure your aquarium's healthy. So it's the same thing. We test it for our drinking water as well. Same thing with the next one, phosphate. We're gonna be using chemicals. You're gonna put the water sample in, add some chemicals, shake it up, add some more chemicals, and then check the color. So nitrates are good for plants. Plants love nitrates. We don't need nitrates like that. Too much of it will make us sick. Some of it we can find naturally in the environment. There's stores of nitrates in the soil. Those are okay until runoff from rain pushes them into our drinking water. But our main sources of nitrate pollution is from us, from humans. We add fertilizers to our lawns or to our crops that we grow on our farms. And then when it rains, all those fertilizers get washed into a stream. If you have a leaking septic tank or leaking sewage pipe, that releases nitrates in the water. And once you have an area like a lake or a pond building up too much nitrates, you have too much plant growth. And that doesn't sound like it's actually a thing. But if you've ever driven by or walked by a pond that has too much nitrates, usually it looks like there's this green slime on top of it. And that's all algae. And too much of that blocks the oxygen and the sunlight from the organisms below it and kills everything below it. So like the plants take over. Phosphates are similar in that they're important to plants and too much is harmful to us. But the difference is that we actually use phosphates a little bit in our water to protect us against lead. A lot of old piping was made out of lead. And as new homes are built or renovated, they replace the pipes with non-lead sources. But there's still plenty of homes and businesses out there that have older pipes in them. And the way they counteract that is by adding a little bit of the phosphates. And the phosphates help block that lead so we don't get sick. But usually it's so low that you can hardly detect it in your testing. It's supposed to be very, very little bit of phosphates in the water. If we have a contamination in our water sources from phosphates, it usually comes from humans. But it also can come from animals as well. So human or animal waste, which means poop. It can come, there's a lot of phosphates in laundry chemicals or cleaning supplies. So when those get dumped in the drain, they eventually make their way back to the stream. And a lot of industries, their byproducts tend to be full of phosphates. And if they're not contained properly, they can lead to contamination of water. So if you're running a business, especially an industrial type of business, you gotta be very, very careful about how your waste is managed, because the EPA will slap a big fine on you if you do something that can contaminate the water. Does anybody know what I'm talking about when I say salinity? Not salinity, no. Salinity. So what if I told you that ocean water has a higher salinity than fresh water?
Like salt.
Salt. So knowing the salt level of water is important. Because if you didn't know already, you cannot drink ocean water, you will get sick, and you will not survive on it. So if you're floating around the middle of the ocean, don't drink the ocean water. It'll make you die faster. Don't do it.
What if it gets into your mouth? How does it make you sick?
Because it's just a little amount. I'm talking like, I got nothing else to drink, so I might as well drink, nice cold glasses of ocean water. Don't do that. I mean, for real. So salinity, we're not gonna talk much about salinity because it's pretty basic. It's how much dissolved salt is in the water.
Yeah, because everything H2O is in water.
So for ocean water, on average, and a lot of oceans are different, a lot of seas are different, but on average, ocean water is 35 parts per thousand when it comes to salinity. And what that means is for every 1,000 grams, for every kilogram of ocean water, there is 35 grams of that is straight up salt. That's a lot of salt. As a contrast, our fresh water, like river water, has to be below 0.5 parts per thousand. So less than half a gram for every 1,000 grams of water. Otherwise, things are going to start dying. It's probably going to taste weird. It may not kill you right away, but it's not ideal for drinking. Plants and organisms that live in waters with higher salinity have adapted to live there. Other organisms, if you take a freshwater fish and put it in ocean water, it's going to die. It's not adapted to live there. Same thing for a marine fish. If fish that lives in the ocean, you move it to a freshwater lake, it's going to die. They've adapted to their particular environments, which includes the salinity. All right, we're moving on from chemical factors of water. Now we're talking about bioindicators or biological factors. Bioindicators, bio means life, so this is an indication of life, signs of life. And we especially pay attention to what are called macroinvertebrates. Big word. Macro means big. Invertebrates means animals without a spine. And when I say big, I don't mean like horse big. I mean like big enough that we don't need a microscope to see it. So crayfish, snails, insects, worms, those types of things. Believe it or not, they are a great way to tell if water is good or not. The snakes have spines. This is the last bit. So, one of the cool things I wish we could do, one, it's the wrong time of year, and two, we don't have any water sources that are good for us, is to go out to water sources with a skimmer net, which is like a really, really fine net, it's not a big net, and you scoop the water. Not paying too much attention to each other. You skim the water, especially along the shore, and you look for these macroinvertebrates. And you're looking for a variety of them. You want to know what types there are out there. You want to know how many of each type. And you want to know their condition. Like, are they healthy or are they sickly looking? Are they weak? And the reason is that these macroinvertebrates, these organisms, they are sensitive to pollution. That means that if there's pollution in the water, they're going to be affected immediately. They'll start to die off or they'll be sick. So if you're at a water source and you're trying to collect macroinvertebrates and you're having trouble finding them, there may be something wrong with that water. The more of a variety you have of these type of organisms, usually the better the water is. That doesn't mean that you can drink it. It means it is good water for the environment. Part of what our lab will include, starting tomorrow, is looking at microorganisms, not macro, but micro. That means that you need a microscope to really be able to see them. So I've got several slides water, freshwater microorganisms that you will be investigating tomorrow. And I would like to, ideally, we would get a sample of like pond water and we put a drop of it under the microscope and see what we can see moving around in there. But this time of year, you're not gonna see anything moving because it's too cold. So what I've ordered is kind of like dehydrated pond water samples. You add water and the things that were dormant come to life, and then we can look at it under the microscope. So I'll have to see when that's gonna arrive. What are you gonna do when you're done counting down these notes? Is you're going to fold these and put these in your notebook. Yeah. Wait till everybody's finished. You got some people copying.
Can I go now?
Yeah, you're good. Fold these papers and put them on the page 455. Keep on the page.
Comments. Does it have to be about water?
No, it needs to be about problems in our area. So you think about things that we touch on, what issues we have in our area, and then what can we do?
Oh, yeah.
So it can be about water relation, or about something different. As long as it fits that theme, that's fine.
These comments. Can I see that?
When, oh wait, she's done, yeah.
What are you doing?
All right. While you are gluing those in and updating your table of contents. Water quality. You need to not talk, you need to listen to the video, because this is gonna help you with our next activity. Gentlemen? Thank you.
Are closely tied to the centerpiece of this whole water quality puzzle, pollutants. Some water pollutants are easy to see, like garbage, but the most serious pollution problems aren't as obvious. Sediment, nutrients, chemicals, pathogens. Sediment is simply soil. It's a valuable resource in a farm field or along a stream bank, but it becomes a major problem when it's washed into waterways. At the root of the problem is erosion.
Erosion off of farm fields, construction sites where you don't have proper sediment control structures in place. You can easily have sediment eroded off those landscape areas. You can have pasture areas that are overgrazed, animal access, cattle access directly to streams. With all of the trampling along the stream corridor, that exposes bare ground, which in turn exposes sediment to erosion. And then along all of our major rivers, if you don't have a lot of vegetation sort of holding the soil in place, stream banks can be a major source of sediment.
Why is soil so damaging when it's in water? It affects everything from the way water looks to what can live in it. Sediment can block sunlight, influencing what types of vegetation and species can thrive in that water. Sediment fills in waterways, affecting transportation and recreation. And sediment can be a carrier for other pollutants, like toxic chemicals, which attach to the sediment, making it a double threat. Next are nutrients, which pose an entirely different problem. Nitrogen and phosphorus are natural components of manure, human sewage, and decaying organic matter like leaves. They're also present in manufactured fertilizers. Nutrients are applied to farm fields to feed crops and to backyard gardens. They're used to green up golf courses and lawns. They become a problem when precipitation washes nutrients off the land and into waterways. Once they're in water, they do what they do on land. When we have too much nitrogen in the water tends to turn green and there's a lot of algae blooms. When those algae blooms finally die and the algae start to decompose, they take up all the oxygen in the water. And so there's a low amount of oxygen in the water, which causes problems for fish and plants because they need that oxygen. Nutrients aren't just damaging to water ecosystems, they also pose a real risk to humans. Nitrates, a byproduct of nitrogen, are especially dangerous.
When we have too much nitrogen in drinking water, for instance, babies, maybe infants under 6 months of age, can develop something called blue baby syndrome. And what that is their blood can't carry enough oxygen, and that can cause some health problems. And in fact, we may have older people or people who are in poor health that can also have that problem.
The risk is so serious that the Environmental Protection Agency, EPA, tightly regulates the levels allowed in drinking water. Chemicals are another class of pollutants. Some chemicals commonly used in manufacturing, mercury, PCBs, lead, are toxic to the environment and humans when they reach certain levels. Because of the health risks these chemicals pose, the EPA carefully regulates industrial waste. Special permits govern the disposal of toxic chemicals, but spills, accidents, and improper disposal mean they still get into waterways. The problem isn't just industrial either. Think of the toxins around your own house: cleaners, paint thinners, pesticides, oil. Improper disposal of just 1 gallon of oil can impair 250,000 gallons of water, about the amount of water in this pool. Agriculture also relies heavily on chemicals like herbicides and pesticides. Their application needs to be carefully controlled to prevent contamination of water. The list of chemicals we use every day has grown faster than our knowledge of how they interact with the environment. Emerging contaminants, a buzzword in water circles, looks at chemicals not traditionally tracked like caffeine, over-the-counter drugs, antibiotics, and disinfectants. A study completed by the United States Geological Survey found levels of many of these contaminants in streams across the United States. Now, the real work begins to see what, if any, effects these chemicals have on water quality. Pathogens are probably the most serious threat to our health. Pathogens are disease-causing bacteria and viruses. They can come from human sewage or raw animal waste. If pathogens contaminate water and aren't eliminated during treatment, the tiny organisms can kill.
One of the real risks that anybody faces who treats water either to drink or as we do, to make in a condition that can be returned to the river so fish and wildlife can use it and so other people can drink it, is killing certain kinds of viral infections or bacteria.
All right, on your desk at each group
Practices
is a plastic baggie that you are going to sort into 2 piles. Now, after benchmarks, you guys had a reading where you were supposed to highlight. Thank you. You had a reading where you were supposed to highlight and answer like 9 multiple choice questions with it. And in that reading included information about point and non-point sources of pollution. I've given you the definitions up on the board. Your job right now is going to be to sort those 2 piles into point and non-point sources of pollution. I will tell you that you will not have an even number on both sides. Work together with your group and see how close you can get. Split those up. If you don't feel the need to participate, I can feel the need to help you out tomorrow instead of doing a lab. That's the typo, that's. Almost gave me.
I know that. Because I can't read it. You know, typed down. But I can-
After your group feels like they've got a pretty good answer going, they've got 2 piles separated and you feel pretty good about them, go ahead and write down the definitions in your notebook underneath the notes we just took, just like you see, we need them side by side. So that second page that I handed out, at the bottom of that second page, write these 2 definitions side by side, because you're gonna need to put stuff underneath them.
I probably do it. After y'all have sort those, you feel pretty good about it. You're gonna write down those 2 definitions side by side at the bottom of that second page I handed out. You should have plenty of room to write on the bottom of the second page. Have them side by side so you have room to write stuff underneath. Right, so after y'all feel like you got a good sort going on, you should write those down. Yep, just side by side, just like you do. And you feel like you got a good file going. After you finish with those, write those definitions down. Yep. Y'all feel like you got a good? Write down those definitions. Yeah, too many point source pollutions.
kind of big. You can always put this on the back of your paper because you're supposed to fold it in and like.
It's gonna be on the, what's that called? Yeah.
Yeah, what we did there. No, the, usual mine was there. All right. Just walking around, a lot of you are getting some of them right at least. Some of you are getting more right than others. Gentlemen, thank you. So somewhere in your notebook, after the water quality notes we just said, if you can fit it in at the bottom, if you write small, that's great. If not, put it on the back of your paper, it doesn't matter. Just somewhere you need to write down the definitions. And these are the correct answers. You need to know the difference between point and non-point sources. You need to know lots of examples. So, point source pollution. What you need to remember. What's she talking about? She said, write this down. Move up here again if you need to. I think that's going to be a thing anyway. So point source pollution. Just think about if you're able to point, like it's your fault, you're polluting. It's point source pollution. If you can't figure out the exact spot where it's polluting at, it's non-point. So a damaged pipe. You can go, yep, there's that pipe right there. Causes the pollution. So that's point source. Raw sewage from water treatment plants. If you can go to the water treatment plant and go, yep, look at that. That treatment plant right there is doing it. You can see the source in which it's flowing into the water. Bless you. Release of chemicals from a paper mill. You can go to the paper mill, you can see where the chemicals are dumping out at. Yep, right there. Point source. Dishwater release from homes. This one is a little ambiguous. It can pretty much go into any category depending on how big of an area we're talking about. If you're talking about a ginormous subdivision and you don't know exactly which part of the subdivision it's coming from, it could be non-point. But if you know which neighborhood, you can go, yep, this neighborhood right here, these houses right here, I can see it entering the water right here. And a lot of times you can see because it's dishwater. You can see it coming from pipes, makes the water all bubbly looking. Heated water from Duke Power Plant in Blues Creek. Anybody ever been swimming in Blues Creek? The lake? Not the creek, but the lake. So it is a lake that's kind of warm all year round. Like you can go swimming a lot later in the season than you could any other lake. And that's because they use water to cool off the heated components of the power plant. So they bring in water, they cool off the pipes, and then the water gets pushed back out in the lake, which makes the lake water warm. Which is fun for swimming, but bad if you're trying to keep certain organisms alive because the water's too warm. So even though it's just hot water, it's considered a pollution. It's not natural. And they know exactly where it's coming from. We'll pick this back up tomorrow. Make sure your little papers are put back into your baggie so they don't get lost. Mix them up, make it a little difficult for the next class to figure out. And then y'all may go. Hopefully I'll see you tomorrow.